Okay, so my project is DysonFan and FLUENT. Username is DysonFan, so you can grade me. Presentation outline, I'm going to cover problem definition, creating the geometry in SOLIDWORKS, meshing it, getting it into ANSYS, a failed trial, solving it in FLUENT, finally what I did to fix that, results, conclusions. So Dyson products and the inspiration was their vacuums, obviously, that's what I wanted to do. They also make little vacuums, hair dryers. Here's their fans. So this is a little bit more simple than a vacuum, so I'm going to focus on these little fans. This is how they work here. They have an airfoil, and the air is collected through the bottom, forced out through the airfoil as a convergent divergent nozzle, basically. High-speed air, and then it induces a flow on the surrounding ambient air. Existing models, there are, this is a really advanced 3D model. This is an ANSYS 2D tutorial that I did, and I wanted to see what I can do with a 3D model. So the problem definition, the original intent was to check out how different turbulence models affected the flow of the fan, and actually this later was changed because of complications. So SOLIDWORKS, getting this thing made, found a patent that had a profile, and I just sketched over the top of that, made a 3D body, and then from that, subtracted that from the fluid region I was interested in. The mesh in ANSYS was really complicated. It's really dense around that fan, and it's a 3D mesh, obviously, so we're going to look really closely at this detailed area, which is the fan. You can see that some of my issues were that the curvature of this, you lose some of those finer features with the elements crossing over it, and we only have one element through this thickness, otherwise the number of elements went through the roof. So, problem definition, 2 out of 2. We have pressure inlet, and we have a pressure outlet. We have 4 walls, an inlet into the fan, and then we also have wall boundary conditions on the fan itself. So the first trial was horrible. The error I got was divergence in AMG solver, kept popping up. After 8 hours of running simulation, it would just say, no, couldn't do it, sorry, no results, no nothing. So I ended up having to split up the model. This was the model before, one body with the internal part of the fan and the external flow. So I broke that up, internal only, external only, and so hopefully that thing together added up was the correct model. So running that internal flow only just forced that mass flow rate right into the fan there. And part of my issue probably was that around this ring, I would get high velocity zone right at the inlet, obviously there, and not at the top, so that high-speed air wasn't actually coming out of the top, as much as the bottom anyway. So here is some videos of that profile, some decent slices of that as it goes. I'll pause this left one, and this is the ISO surface, probably not super usable, but you can see that the high velocity area is that bottom part of the ring there. Moving on, again, like I said, I have that part of the model opened up on the bottom, whereas what it really is restricted there, probably increases the flow and gets it up to the top part of the fan. But I'm using, for the external model, what I'm really interested in is 25 meters per second velocity, which is a 55 mile an hour flow out of the fan, and we'll see how that affects the system. So it's the same boundary conditions as before, and then that area there is where that red bar was. Okay, so let's solve this external model. Forcing parameters in FLUENT. So to actually get them to solve, we need to apply different boundary conditions, but it finally ran. An oversimplification required that we didn't do any turbulence, so it was laminar only, and then that means that the whole goal of the project is out the window, because we can't get any effects of turbulence. Instead, we'll just look at the results, and we'll just be happy that this thing actually ran. So the results, here's a residual plot of velocity out. We're going to take snippets at 50, 100, 300, and 500 iterations, and compare those videos real quick. So here's an ISO surface, probably not really useful, but there's 50 iterations, 100, 300, and 500, top left, bottom right. And you can see that there's a high velocity field before in this top left one. That's because our outflow is stuck at that initial condition of 55 miles per hour to get that flow in the right direction. Otherwise, it would not solve. So that's an unrealistic thing. But it finally stabilized to around 5 meters per second out as a constant flow, which is really cool how that fan consistently induced that flow through the whole field. And so here's the final video. You can see the velocity profile. You can see that high velocity front, and then as this thing develops and solves and converges to a steady state solution, the final one doesn't have a whole lot of change. And conclusions from this: if the goal was to determine turbulence models and their effects, a 2D model would probably be more appropriate for computation's sake. A 3D model has more physical meaning, but it's extremely computationally expensive. And then increasing the number of elements in a 2D model would be less detrimental as compared to a 3D model. It is better to achieve a good 2D mesh than a less physical, meaningful 3D mesh in a model that doesn't work. So that's really all I got. This is, again, just in case you needed it.